6.6, operations with algebraic vectors in R squared. Okay, so let's recall. In R squared, we show vector OP, so that's from the origin to P, equals AB. Okay, and this was a vector formed when we joined the origin, which is 0, 0, to the point P, AB. Okay, so the exact same thing can be applied to R cubed. Okay, from the origin, 0, 0, 0. So all we've done is extend it by one coordinate in the coordinate system, so the Z, or the Z, okay, to the point ABC. Okay, and that C is now our Z. Okay, so writing position vectors in terms of unit vectors. Another way of writing vector OP, which is AB, right? So we would write it with brackets and then A comma B, is with the use of the unit vectors I and J. The vectors I, so 1, 0. So all this means here, so this is a unit vector. If you can see the red right here, I'll do it in red as well. Okay, I is 1 unit, so this is 1, 2, this is 3, and this is 4. So I is 1 unit long, magnitude 1, and it is only in the x direction. That's what a unit vector is. And remember, unit vector is 1 unit long. Okay, that's it. Okay, and now J, so J they wrote in green. Okay, J is 0, 1. Go a little darker. So if we go up 1 unit, okay, don't count boxes, count units, because the scale is 2 boxes is 1, so every dash is going to be decimal 5. Okay, and we're going in the y direction. So magnitude of 1 in the y direction, that's the unit vector J. Okay, and these lie along, of course, the positive x and the positive y axes. Now, vector OP is -3, 8, can also be rewritten as -3i, -3 of vector I plus 8 of vector j. What does that mean? So that means in the I direction, we're going -3. Oh, you know what? I'm going to change this to +3. I apologize. Because this goes +3 in the I direction. I think this is a different example. So this is going to be like 2.2. Let's call this 2.2. So this would be 2.2 up. So this right here for P, so vector OP in this diagram, we can either rewrite it as 3, 2.2, or we can write it as 3 of vector I, right? 3 going in the I direction, the x direction, plus 2.2j. Okay, 2.2 going in the y direction. Okay, and then this was just another example. 3, 8 can be rewritten as 3 vector i's plus 8 vector j's. Okay, and then what this allows us to do is write all vectors in terms of I and j. And again, each representation is unique. Okay, so example 1. For position vectors, vector OP is 1, 2. So OP is 1, 2. 1, 2, it's OP. OQ is -3, 0. So OQ, -3, 0. OR is -4, -1. So we go -4, -1. That's from the origin to this point, R. And OS is origin to S, so 2, -1. So these are shown in the graph. So what we're going to do is we're going to write each of the vectors using the unit vectors I and J. So we're going to write vector OP, then we're going to write vector OQ, and then we're going to write vector OR, and then vector OS. Okay, so we can take a look at the graph, or we can just simply read the actual point off. So vector OP is 1, 2. So that means we're going to have 1 in the I direction plus 2 in the J direction. OQ is negative 3, 0. So we can either write this as negative 3 vector I plus 0 vector J, or we can just simply write it as negative 3I. So you just have to pay attention when you're reading these in component form, like in this form here, because sometimes they'll leave out a letter, so you just have to organize your thoughts there. Okay, OR, we're going to have negative 4 vector I's minus 1 vector J. And OS, 2 vector I's. And then instead of writing negative 1, I'm just going to write negative J. Okay, because you can see negative 1J or you can just see negative J. Same idea. Okay, so B. The vectors OA equals negative vector I. Okay, I'm not going to read these. We have vector OB, vector OC, and then vector OD. Have been written using the unit vectors. Write them in component form. Okay, so sorry, I think I made a mistake. This is component form A comma B. Okay, and then this is them written using unit vectors. Okay, so if we have vector OA and it was negative I, well, I is in the X direction, so we're going to have negative 1, and there's no J, so we're going to have 0. Okay, so let's write component form for OB, OC, and OD. In vector OB, we have 1I plus 5J, so that's the component form 1, 5. Vector OC is negative 5I plus 2J, right? And vector I, vector J, of course. So negative 5, 2. And OD is root 2 vector I, so we have root 2, minus 4 vector J, so negative 4. Addition of two vectors using component form. So what we do is we start by drawing the position vectors OA, so wherever that leads to, so say some number AB. So OA would go here, right, tip to head, and OD would be, say, CD. So OD would be here to here, right, tip to head. But we know that even like the angle between these, it's not going to be the angle we actually use. We need to pick up B and go tail to tip, and then we have to consider the resultant. Okay, so this is going to be the resultant. So when A and D are any 2 points in R squared, then rewrite each of the two position vectors. So what we're going to do is we're going to write the position vectors, and we're going to go from component form A comma B to unit vector form. Okay, A vector I plus B vector J. And then likewise for OD, it's going to be the same. We're going to go from CD to C vector I plus D vector J. Okay, so what will happen is the magnitude of OP, so the origin to any point, just in general, is A squared plus B squared all square rooted. Okay, so let's just take a look at this little blurb here. Adding two vectors in R squared to determine the sum of two algebraic vectors and their corresponding X and Y components, all we do is we just add the components. So we add the X's, so A plus C, and then we add the Y values. X's, Y's, B plus D. Okay, so to determine the sum of two vectors, add their corresponding X and Y components. So if OA, so vector OA equals AB, which is A vector I plus B vector J, and then OD is that CD, then when we add the vectors OA and the vector OD, what we do is we add the x values, which is a plus c, and we add the y values, which is b plus d. Now, likewise, the exact same thing, but when we're finding the difference, so when these vectors are subtracted from one another, what we do is we subtract their corresponding x and y components. So I'm not going to reread the components of OA and OD, but when we subtract them, we do A minus C, and then we do B minus D. Okay, so just take note here, we are doing vector OA, which is this A component and this B component, and we're subtracting OD. So it has to be in this order. We have to subtract the X component of OD, and then we have to subtract the Y component of OD. Okay, now to determine the product of a vector and a scalar, all we do is multiply each component of the algebraic vector by the scalar. So, in other words, if we have some scalar m times vector OP, all we're going to do is we're going to write m and then the component form, AB, and we just multiply A by m and then B by m. Okay, and we get MA comma MB. Okay, now multiplying a vector by a scalar in R squared. Okay, so this is kind of a continuation. To multiply an algebraic vector by a scalar, we multiply both the x and the y components by the scalar. So, for example, if we had some point AB, so this is going to be vector OP. This looks like it's 1.5 times OP. So we go in the same direction, we just go another half time. So O, let's call this Q. Okay, OQ would be 1.5 times vector OP. Another scalar, so this is like what it would look like if it was a positive scalar. Okay, so this one is a positive scalar. Right, if m is greater than 0. Now, if m is a negative scalar, what happens is we turn it around and we're going the other way. So same magnitude, just different direction. Okay, so given vector A, so vector OA is 1, 3, and vector B, but all this is telling you again is that vector A and vector B were repositioned and they actually are written from the origin. Okay, so 4, -2. Determine the components of vector A plus vector B. Okay, so vector A plus vector B, I'm going to add the x components, which is 1 plus 4, comma, then I'm going to add the y component, which is 3 plus -2. Okay, so I get 5, 1. Okay, so it's vector A plus vector B. That's it. Now, vector A minus vector B is going to be 1 minus 4, comma, 3 minus -2. And really be careful of that double negative. Okay, so I get -3, 5. Okay, and now this question wants us to illustrate each of these vectors on a graph. So I will draw a graph here. So if we have 1, 3, so I'm going to go 1, 1, 2, 3, 1, 3, and I need more room. All right, so we go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 1, 2. Okay. So when we add them, so vector OA is 1, 3. So it's like 1, 3. So that will be the head. Okay, and then OB is 4, -2. So we got 1, 2, 3, 4, -2. So this here will be the head. And all we do is we pick this up and we attach it, see, tail to tip and then tail to tip. So basically, this is OA. So this is vector A. If we start here and we go in the x direction 4, so 1, 2, 3, 4, we do land at that 5. And then if we go down 2, right, so the y component is down 2, it's essentially like we picked up this vector B and we attached it to the tip of vector A, and then this is going to be our resultant. So our resultant is here, and we can clearly see that the resultant is 1, 2, 3, 4, 5, 1. So this is the resultant, vector A plus vector B. Okay, and I'm just going to write vector B here. Okay, for the second one, so 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. 1, 2, 3. Okay, for the second one, we have vector A. So vector A again is 1, 3. So this is vector A. And vector B is 4, -2. 1, 2, 3, 4, 1, 2. It's just like plotting coordinates, but then where we plot the coordinate, we just plot the arrow and then create the vector. Okay, so then what we want to do with vector A and vector B is we want to add or subtract vector B from vector A. So instead of going, say, this way, we're actually going to go the opposite way. So instead of going to the right 4, we're actually going to go 1, 2, 3, 4 to the left, but then still up 2. I wanted to do that in purple. Go. Okay, so this is negative vector B. So then our conclusion here is this is vector A minus vector B, and we can clearly see that it's -1, -2, -3, 1, 2, 3, 4, 5. -3, 5. Position vectors and magnitude in R squared. So when we consider a vector, say for example, vector AB, note there's no origin on this, okay? A little bit different. We must also consider its related position vector and calculate the magnitude of vector AB. To do this, we have to use the triangle law of addition, which is similar to finding the distance between 2 points. So essentially Pythagorean's theorem. So if we have some point A, x1, y1, and some point B, x2, y2, okay, so these are 2 points, then vector AB, what we're going to be doing is we're going to be finding the difference between the x's and then the difference between the y's. Okay, and then this is going to be its related position vector. Okay, and we would call that position vector, say, for example, OP, vector OP. Okay, all that's doing is it's going to take some, for a visual, it's going to take some, say, for example, in this one, A, -3, 7. It's going to take some A value, And say you're doing vector AB, just as an example. So AB, 5, 22. So this is like 5, and then 22 is way up here. Let's pretend it's right here. And it's saying, okay, well, now this is our vector. We're now going from A to B, right? Vector AB. Okay, then when they call this, so we're going to see basically what we get for the X and the Y, or say, for example, the A and the B. What we get for those two components is essentially the difference. And if you think about this, the difference in the rise and then the difference in the run, right? Well, the difference in the run first because it's the X coordinate and then the rise. Okay, we've used a similar method when we were finding, like, remember the distance formula in grade 10? We would do x2 minus x1 and then square it, plus y2 minus y1 and then square it. It's the exact same thing, except for we're not finding the distance. Actually, the distance is the magnitude. It's the exact same formula as grade 10, distance. But for the actual component form for OP, we would essentially just be taking each of these, so x2 minus x1, and writing it in component form. So we'd write the number, and then y2 minus y1, and then write the number. Okay, so then when we're talking about OP, so we have vector AB, we literally pick up this vector, we put it down here, and then this would be called OP. This is our position vector. As a recall, position vectors are at the origin. Okay, they start at the origin. So it's just that you pick it up, okay, congruent size, congruent shape, congruent angles, you pick it up and you reposition it at the origin. So example 3, we have A, B, and C. These are points. Please note that there's no vector notation above A, B, and C. Okay, so they're just points. These are 3 points in R squared. Okay, 2 dimensions. That means we're just dealing with an X and a Y. So A, we're going to calculate the magnitude of AB plus the magnitude of BC plus the magnitude of CA. Okay? So if we had these 3 vectors, it would essentially be the perimeter of a triangle, say ABC. So let's solve for that. Okay, so let's go. First, we're going to find vector AB. So we're going to subtract the X components for B minus A. Okay, we always subtract them backward for to find the position vector. So this is essentially 5 minus -3. And then we're going to go 22 minus 7. So 5 minus -3 is 8. 22 minus 7 is 15. So vector AB can be rewritten as 8, 15. Now the magnitude of vector AB is going to be 8 squared plus 15 squared. Okay, we already did the legwork. We already did the x2 minus the x1 and the y2 minus the y1. So we don't have to rewrite it. Okay, so 8 squared is 64. And then 15 squared is 225. And when we add those up, we get 289. And then when we root them, we get 17. So, say for example, in this triangle, vector AB is going to have the magnitude of 17. Now, vector BC. So let's subtract the components C minus B. So 8 minus 5, 18 minus 22. Okay, so 8 minus 5, we get 3. 18 minus 22, we get -4. Okay, so that is vector BC. Now, if we're finding the magnitude of vector BC, what we want to do is we want to do 3 squared plus negative 4 squared, okay? Just like Pythagorean's theorem. So 9 plus 16, which is 25, and when we root that, we get 5. So vector BC, we get 5. And remember, Pythagorean's theorem works because now if we have some vector, we're going up a certain amount and across a certain amount. So now we're kind of looking at it like a right angle triangle. We're looking at it in 2 different components. We're looking at it in the I component. Wait, up and down. Sorry, that's J. And the I. All right, the X and the Y. Okay, now we are going to do vector CA. Okay, so we're going to go A minus C. So negative 3 minus 8 and 7 minus 18. Okay, so I get negative 11 and then 7 minus 18. I think it's the same, negative 11. So that's vector CA. And the magnitude of vector CA is going to be the square root of 11 squared plus 11 squared. Here's the thing. It's technically negative 11 squared, but regardless, negative 11 squared and 11 squared are going to yield the exact same answer because anything squared is going to yield the positive result. Okay, so 11 squared is 121. Plus 121, I get root 242. And when we root it, you know what? Let's do this as a decimal. That's fine. Let's go 15.6. Okay? And we can say units because we don't know what the units are measured in. The question didn't give it to us. They didn't say kilometers or meters or whatever. So we just write units. So this is going to be 5.5, or sorry, 5.6. So we can say for our concluding statement, the magnitude of vector AB plus the magnitude of vector BC plus the magnitude of vector CA is going to be 17 plus 5 plus 5.6. And then all we do is add them together, and we get 27.6. 27.6 units. Sorry, this is supposed to be 15. So this is 37.6 units. Is the perimeter of triangle ABC. Okay, now we have calculate the value of AB plus BC. So vector AB, let's do this, vector AB plus vector BC. And that's the magnitude. Okay, so what we want to do first is we want to write out in component form vector AB. So vector AB again was 8, 15. And we're going to add vector BC. So vector BC is 3, negative 4. So 8 plus 3, then we have 15 plus negative 4. Okay, so we have 11, 11. Okay, and we kind of just figured this one out, so let's do it again. So this is going to be the magnitude of AB plus BC, and it's going to be root 11 squared plus 11 squared, which is the 121 plus the 121, which is the root 242, which we get the 15.6 units, okay? Because it's the same calculation as this right here. What does it ask? Nope, just the value. So 15.6 or 15.6 units. Okay, because this one just asks for the value, we don't have to put units. Okay, example 4. For the vectors vector x and vector y, okay, and then this is giving it to us in the unit vector form. We're going to determine the magnitude of vector x plus vector y, and then the magnitude of vector x minus vector y. So let's first add vector x plus vector y. So we're going to add the 2i plus the negative 4i. Sorry, this is I. Okay. Then we're going to write negative 3j, and then we're going to add negative 3 vector j. Okay. And please note, this I and j, this unit vector form, doesn't have a comma there. It's kind of like an equation. It's like 2 vector i's minus 3 vector j's. Whereas the component form would have simply been like 2 comma negative 3. Right? This one's more of an equation. So what is 2 minus 4? Well, I get negative 2 vector i's. And then negative 3 minus 3, I get negative 6 vector j's. If we want to write it in component form, we can just simply do negative 2 comma negative 6. Okay, now the magnitude of vector x plus vector y is going to be that negative 2 squared plus that negative 6 squared, which is going to be 4 plus 36, which is going to be root 40. Okay, root 40 or root 40 units. It is a magnitude, so it is a length. Okay, root 40 doesn't simplify. We could pull out of root 4, but we can leave it like that. That's fine. Now, let's do vector x minus vector y. So let's do 2 vector I minus negative 4 vector I. Then we're going to have plus negative 3 vector j, so we can just put minus 3 vector j, minus negative 3 vector j. Let's put equals. So 2 minus negative 4 is going to be 6 vector i's. And then negative 3 minus negative 3, those go away. So in other words, 6 comma 0 is going to be our component form. So I can already tell that 6 comma 0 is going to look like this. It's going to go 6 in the positive x direction, 0 in the y direction. So I can already tell that the magnitude is going to be 6. But if you're not comfortable with that, what we can do is we can actually formally solve 6 squared plus 0 squared, which is going to be 36, obviously plus 0. And when we root it, we're going to get 6 units. So we're going to get the same thing. Okay, example 5. If vector A is this, vector B is this, and vector C is this, let's calculate the magnitude of, so let's go vector A minus 3 of vector B minus 1/2 of vector C. Okay, so vector A is 5 comma negative 6 minus 3 times vector B, which is negative 7 comma 3, minus 1/2 of vector C, which is 2 comma 8. Okay, let's distribute those negative 3 and the negative 1/2 into the bracket. So we have 5 comma negative 6. Okay, so I'm going to put plus, and then I'm going to distribute the negative 3 into the bracket. So this negative is kind of like plus negative 3 times this, right? So because I'm distributing the negative 3 into the bracket, I can put a plus here. So I get 21 comma negative 9. plus, same thing here, negative a half times 2 is negative 1, and negative a half times 8 is negative 4. And now we add the components. We add 5 plus 21 plus negative 1, comma, and then we go negative 6 plus negative 9 plus negative 4. So 5 plus 21 minus 1 is 25, plus negative 6 minus 9 minus 4 is negative 19. Okay, so this is vector A minus 3, vector B minus 1/2, vector C in component form. And now, when we want to find the magnitude of this, we simply do the 25 squared plus the negative 19 squared. And then we square root it. So we get 625 plus 361 which is 986 square rooted. So we can either leave it like that or we can round it to 31.4 units.